Welcome to the final lecture this quarter, in which we'll go over IR sensors, which allow us to see the maze. And we'll talk about how we enable the wrap to do that. So just a quick overview. So let's go over what the IR sensors are and why and how they work. We'll go over the circuit in which we implement them, along with the receiver circuit. So basically, how do we send out IR pulses and then also receive them and read their values. And then we also go over the software part in which we implement it in our code.
Okay, so first we're just going to go over the basics of what IR sensors are. Actually,
yeah,
sure. Okay, so and the way that an IR sensor works is essentially that it has two components, an IR receiver and an IR transmitter. And the way that these work together is that the IR receiver sends out, the IR transmitter sends out a pulse of IR infrared light, which then bounces off any objects that are nearby, and the receiver can pick the bounced light in it. And basically what happens is if the object is closer to the receiver transmission or receiver transmitter pair, then the value that it reads will be significantly higher than when it's further away. And the intensity that the IR receiver reads is proportional to 1 over the distance of the object squared. So this basically means that, like, for the purposes of Micromouse, since the distances that we're going to be measuring are very small, the IR sensor can provide a good measure of the distance from how far away you are from, like, a wall or a different object.
And so why do you want to use IR sensors? So you might be thinking, okay, you guys probably have heard about ultrasonic sensors. The problem with them is that they are big and bulky, and imagine having 3 of them on your small rat robot. That is just unfeasible. So on the other hand, IR sensors are much smaller, so you can see that the pairs right here. So you can fit more of them, and they perfectly serve our needs. All they need to do is just detect if walls are there. So they're easy to implement with relatively few components, and then they're more. And so you also don't have to touch the walls to know that there's a wall. So you can just detect a wall without having to go right next to them, like a bumper switch or a touch switch. And they also give us an analog value. This means that instead of giving us a 0 or 1, they can give us a wide range of values, and this allows us to set a threshold number as detecting if there is a wall there or not. For example, say 700, 650, some number you can experimentally determine.
Okay, so continuing on with some of the cons of IR sensors. The first and the main one that you're going to be experiencing in Micromouse is that they are very sensitive to ambient light. And now what this means is, like, if you're trying to run your Micromouse outside in the sunlight, it really will not work at all because the sunlight contains a lot of IR light in it and it will just, like, mess up the sensors. This applies to, like, if the windows are open as well and it's, like, really bright outside and, like, the light is coming in, it might not work well. Certain light sources, like I said, can also affect IR light. Now this also means that every time you switch rooms with the Micromouse, you might have to recalibrate the IR sensors, but we'll get into that a bit later on. And again, like I said, another con is that they require calibration to work. Now what this means is, like, whenever you want to, like, use it in a new environment, you're gonna have to recalculate the thresholds for, like, detecting whether or not there's a wall. And finally, it also has non-linear scaling of distances, which means that, like, it's really hard to use it as or it's not really hard, but, like, we generally don't use it to measure distance accurately. We're just using it to, like, detect whether or not there could be a wall in front of it. And also another con is that between different IR sensors, there is variation. Like, for example, one IR sensor could be reading, like, a value of 700, whereas a second IR sensor could be reading, like, 1400 for the exact same distance. And also, if there's, like, different materials that it's trying to read, including colors, it will read different values as well.
So now it's time to go into the analog IR emitter circuit. So just to clarify, go back to the previous diagram. You see them come in pairs. So basically, you need one IR emitter to emit the infrared light, and then you need one IR receiver to pick up that emitted infrared light and read its value of how much returned back. So going to the emitter circuit, what takes the slides? Okay, so this is a very big diagram. Don't worry, we'll break it down, go into every single component. So it uses an IR LED to emit the IR light. So it's just like a normal diode for like an LED, but instead it emits IR, that's a special purpose. We need a transistor in order to turn it on and off, which is what we have right here. And this is because the MCU does not supply enough current. So the MCU supplies around, I believe, 10 milliamps, whereas this requires around 100 milliamps. So we want to use directly the battery supply voltage and current. And that's why, as you can see from this diagram, MCU is not enough, so we need to use the battery power. And so the gist of it is how this works is when the MCU pin goes high, so when we tell it to turn on, then that signal will go into the transistor base pin, where it will ask it to, it will then complete the circuit or turn on the switch per se. That's allowing the circuit to be completed. That's then turning on the LED, allowing it to go high and emit IR light. Any questions about this very quick intro to this? We will go into deeper detail in the following slides, but any quick questions? All right.
Okay, so let's go into like a little bit of detail about the specific IR emitter that we're going to be using. Here are just like some specs of the IR emitter. The only ones that you really need to keep an eye out for the most part, are just like what nanometer light it emits. So when you're going to be making your own mice, you need to pick a pair of receiver or a pair of IR receiver and like the IR LED, such that like the wavelengths are compatible. Like for each of them, they're going to have a specific set of wavelengths that they work under. So just make sure that when you're picking the receiver, which we'll go over in a little bit, that it works with the emitter that you pick.
And the reason why we have such a small angle, 15 degrees, is because we don't want the IR light emitted from one emitter to interfere with the IR light or the IR receiver of another side, for say like the front or the other side. So we want to make sure that it is focused in one direction, so we can read the value of a wall, or the distance if a wall is there in one direction. And now MOSFETs. So MOSFETs are a specific kind of transistor, and that's what this is right here. So again, we're the transistor. For a very basic level, it's just kind of like a switch that allows you to turn on and off certain components. And so it controls the current flow through the IR emitter, which is again denoted by this symbol right here. So it allows us to take the 3v3 power and complete the circuit to then go to ground. That's allowing us to turn on this LED. And it is necessary to turn on and off these emitters. We don't want them on the whole entire time. One reason being that, first of all, like keeping some component on for a long time uses up power. Second being that if we have all the IR emitters on at the same time, they will interfere with each other. So for example, maybe somehow the side IR emitters light might interfere with the reading that you want from the front. So we want to make sure that there is no interference, and that's when we want to turn on the IR emitters at specific times when we desire to read from one side. And the MCU pin is what turns on or completes, or is what turns on the is what completes the circuit of the transistor, and thus allows everything to go through.
Okay, so now let's talk about those two weird looking capacitors off to the side that seemingly do nothing but are actually kind of important. So if you remember from your power delivery schematic, there was two decoupling capacitors that were used to make sure that the rest of the circuit received clean 3.3 volt signals. And essentially what these two bypass capacitors do are like they're serving the exact same purpose. They're just trying to make sure that whenever we turn on or off the IR emitter, first of all, it gets a stable supply of voltage from the battery, or just like in general, it gets a stable supply of voltage. And then also it slightly reduces the time that it takes to turn, that our emitters take to turn on, because the capacitors are like right there, whereas the battery could be like further away on the circuit.
And if you would like a rundown of how these actually work using physics and math, you can let me know afterwards, but there's a very high likelihood none of you will understand until you take physics 1C. Okay, now the MCU pin and the resistor that you see right here. So again, the MCU pin is what allows us to turn on and off the IR emitter as it controls this transistor right here. And then this resistor right here, the 100 ohm resistor, this just controls the current flow to the MOSFET gate, because we don't want to we don't want to send too much and destroy the gate and the MOSFET. That's just all that resistor does.
Okay, and finally the last component, well, almost the last component of this circuit is the 47k ohm resistor, and that resistor serves the purpose of a pull-down resistor. Now, what this means is that whenever the microcontroller pin isn't sending a signal to the transistor, we want to make sure that the transistor doesn't stay on because of like some current that's still left in the circuit. So the purpose of this resistor is just to like pull down the transistor to a 0 value or off whenever the MCU pin is off.
And I think one way to think about it is, you know that ground is always 0, you know that, and then assume that we turn the MCU pin off, so that means 0. When the IR circuit is turned on and turned back off, there will still be some charge stored in the diodes of the transistor. And this might, and if we didn't have this resistor right here, so imagine we didn't have it, we can't say for sure that just because the MCU pin is at 0, we can't say for sure that this side over here is also 0. So by connecting it to ground like this via this resistor and this connection, since we know that this is 0, and since we know that we turned off the MCU pin, which is then also 0 volts, we can then conclude that in order for the whole entire path to go from 0 to 0, this node right here must also be 0. So we can then also conclusively define that this must be 0 or ground. And again, just to repeat one more time, if this wasn't here, then there's no way to conclusively say that this is 0 or ground, because there is still some charge stored in the diodes or of the transistor if it wasn't there. Yeah.
So you're saying basically like the resistor allows, like, is it the resistor or is it the connection that allows the charge to go to ground?
It's the connection to ground, but you need the resistor because if you didn't have it, it would just like short circuit to ground, which is why it's also like a massive value for the resistor, so it doesn't like draw too much current from the rest of the circuit.
Also allows the charge that's stored, excess charge that's stored, to be used up.
Any other questions? Yeah.
R2 and R3 serves as a voltage divider, right? Technically.
Yeah.
But it doesn't matter.
Not in this case. I mean, in this case, the purpose of the purpose isn't to serve as a voltage divider. Like its purpose, well, the purpose of R2 is to make sure that like the correct amount of current is, or voltage is given to the transistor, and the purpose of R3 is to make sure that like there's no floating values in between like on and offs. Yeah.
Are there any other questions about this or what we've gone over so far? All right. Okay.
And yeah, like I said, the reason why it's such a high resistance is to keep the current draw low.
Okay, so now we have this resistor above the LED IR emitter. So why do we have that? So that just limits, because the battery power sends a lot of current, so we want to limit that current, because otherwise the IR emitter will go bust. So we need to limit it by using a resistor. So now we just use some simple V equals IR to figure out the ideal, the resistance that we want in the resistor. So VCC, so we're using 3V3, not directly the battery power. And then the IR emitter can handle 1.3 volts. So that means we need to somehow drop 2 volts. And the desired current of the IR emitter is also 40 milliamps. So now we just do the 2 volts that we need to drop divided the 40 milliamps that the IR emitter runs on, and that gives us 50 ohms for the resistor to go prior to the IR emitter. Does that make sense to everyone? Okay.
Okay, so that's it for the entirety of the IR emitter circuit. Now let's go into the receiver circuit. Okay, so the receiver circuit mainly consists of the phototransistor, which you see over there, which is like the actual receiver, and it also consists of a resistor to create a voltage divider to the microcontroller. And the way that we're going to be getting the readings for the IR sensor is by using the microcontroller's analog to digital converter, which will basically give us a scale from like 0 to a really large value. And that scale is directly proportional to how much voltage the phototransistor lets through it. And like that voltage will differ based off of how much light that phototransistor is getting. Or photoresistor, sorry.
Also, one thing to note is the VCC to ground connection will always have the same voltage drop. You will always drop the same voltage from VCC to ground. The thing that this allows to go through is the amounts of current. It permits the amount of voltage as part said. So in between, you can then read the analog reading to see the amount that each transistor is letting through. Are there any questions about this slide? It is a little confusing.
VCC is the same as 3.3 volts, right?
No, VCC is the battery supply, yeah.
Any other questions?
Also, sorry, it is a phototransistor, not a photoresistor. Yeah.
On the last slide, why was it 51 ohms instead of 50?
Okay, so
Specific value.
that's a good question. So I don't know if they sell 50 ohm resistors. Like resistors just have like set values for the most part. So like 51 is just the closest.
Also, as long as you overcompensate, that's better than undercompensating. So you don't want to like accidentally have too less of resistance that would then cause a higher current draw that would then bust the LEDs. So you want to make sure you always overcompensate them and undercompensate.
Any other questions? Okay.
Oh yeah.
With the photo transistor, so basically it like changes. How does the photo transistor affect the voltage again?
Yeah, so based off of how much light or IR light it gets or it senses, it changes the amount of voltage that it lets through it. So if it's like reading a lot of IR light, it will let a lot more voltage go through compared to when it's reading like no IR light. And this voltage value is then read by our microcontroller and converted to like a number. And like you interpret that number as like how far away the wall is. Yeah.
I have filter resistors that do basically the same thing. How are they different?
I think okay. I think one of them like changes the amount of current and one of them changes the amount of voltage. I could be wrong about this, but I'm not actually sure. Yeah.
But we can look more into that and let you know.
Yeah.
Yeah.
So VCC minus VL is voltage across the phototransistor.
Yeah. Or
Yeah.
yeah.
Just know that like just know that the total like the total gist of what you have to know is that the more light absorbed by the phototransistor, the higher your analog readings will be when you actually see them run in your code. And the higher readings mean that more light was bounced back, meaning that there is some object near the IR emitter or the robot in general. That's meaning that there's probably a wall there. And then that threshold value of like 600 versus 650 versus 700 versus something else, 1000, is up to you to decide. Okay, so going more into the phototransistor itself. So this is the spec number of the photo transistor that we'll be using. You'll probably end up using it in your mouse designs too in the winter and spring. So you can just come back to this slide, literally yoink the part from directly from here, and we'll call it a day. And so its best wavelength reading is at 870 nanometers, but it has this much wider range. And obviously, we want to make sure that this is compatible with the wavelength that is emitted by the IR emitter. And it has a 50 milliamp maximum current draw. Don't worry about the max surge, just you want to focus on the max current. And the more IR light that's absorbed, the more current that will pass through Q1 and then to the rest of the circuit. Any questions about that? Please.
Okay, and the last part of this circuit is the voltage divider, which is just like one resistor that goes to ground. The voltage drop over this resistor is also dependent on how much current is led by the phototransistor. And essentially, we chose the value by assuming that the phototransistor will let the maximum amount of current through, and you could just like do the calculations. But if you keep the maximum current draw less than or equal to whatever the transistor will let through, you can just like pick a value of 1.8 k ohms for the resistor. Any questions about this? Okay.
Alright. Okay, so now going over into the software side of things. So there's a bunch to go over. So so you do assignment 4, we'll go over all this in detail plus more. But you will go over how to turn on the emitters, and then how to read from the receivers multiple times, so that way you can get an average reading that you can then use to interpret in your code however you want. Like, oh, there's a wall there isn't, and how do you actually turn that emitter off once you have your readings done, and then now you can move on to the next emitter. So again, you don't want to turn on all the emitters and receivers, or turn on all the emitters at once and do all your receiving or at once. I mean, you can't do that anyways, but you want to just turn on the emitters in quick succession. So basically just do a sweep. So turn on the left, front, right, and then call it, because that way you can make sure that the readings are associated with each particular side rather than having interference from the other emitters.
Okay, so now let's get into a little bit of the wall detection. Essentially, the way that the sensor data looks like is it's like this black curved line, and that doesn't really tell us much about whether or not there's a wall in front of the mouse. So the way that you're going to determine if there is a wall is by literally taking your mouse, start the IR readings, and in your live expressions, you can actually like see what the IR readings are going to be in real time, and you just like place it in the maze around how far away you want from the wall to the point where you wanted to say that there's a wall in front of it, and you just like take note of that value, and then in your code you manually just like change that value for the threshold. So you just say, oh, if this specific sensor measures a value of above like 500, for example, then there's a wall, or then this sensor is telling you that there's a wall. And you just do this for all 4 of the sensors, and that's essentially how the thresholds are determined. Any questions about this?
You can make this curve, but we highly recommend against it, because it will change this as the settings change, like in the environment you're in, so will this curve. So although you can keep the shape of this curve in mind, it's something not at least I wouldn't recommend reproducing.
What does this curve represent again?
It's just the IR value, or like the analog values for, or the analog values that you get from the IR sensors.
So is the vertical axis what you get, and the horizontal axis is the distance from a wall or something?
I think so. I could be wrong about that though, because like there's no label and the scale is kind of messed up.
Yeah, so actually it's kind of like, it's more focus on like this part right here.
Yeah.
So this is meant to be distance, and that is meant to be the reading. But yeah, the axes are off. We apologize about that. We probably should have cropped it. But this is the general shape of the graph. I think you won't actually, so you won't be coding you won't be coding something where like it semi-detects a wall and then it fully detects a wall. Like you won't be doing that. You'll be doing something much more digital, like just like like 0 or 1, but you'll literally be doing 0 or 1. Like you will literally have a function saying like, oh, is there a wall to the left of me? And that will return like true or false, like or rather 0, 1 in C. And so that's why, that's what's indicated in red by no wall detected or a wall detected. So you won't be detecting some medium state. You'll be detecting on or off by like some literal like value. Like if it is less than 700, that means that there is no wall there. If it's greater than or equal to 700, then there is a wall there. Again, that might lead to certain errors over multiple trials, but that is something that you can code to deal with. All right, so some software tips and tricks. So when you first turn on the IR emitter, you want it to stabilize. It won't immediately start sending a stable signal or stable light outwards. So you want that to stabilize, and then the phototransistors also themselves don't react immediately. So you want to give about 60 microseconds for that value to stabilize. And also for the IR emitter itself to send out a good pulse of light. And then once that stabilizes, then you can then take readings, or rather multiple readings over a very quick succession and average them out. And you want to turn on only one emitter at a time. Again, why do we want to do that? Why do we want to do that?
So you don't get interference.
Exactly, yeah. So hypothetically, we don't want the left emitter to be on accidentally and then accidentally artificially make higher the values in the front, which is extremely unlikely, but it's just good practice to not do that. And then also do not read your IR. Okay, so how many of you have started assignment 3A?
Nice.
Okay, so basically in your PID assignment, there is a function that is called every 1 millisecond, which is called systic, and you don't want to read the IR values within this systic function because it can possibly cause your systic function to exceed 1 millisecond, and that will break your code because if it's called every 1 millisecond, but then it takes longer than 1 millisecond to execute, then there's no longer compatibility, so then that will just not make the code run as you properly intended to.
And just to add in a little bit, if you were wondering why we need to wait 60 milliseconds, I mean, that's like basically instantaneous, right? What?
Microseconds.
Microseconds, my bad. The reason why we have that there is because if you want to like make the IR calibration completely automatic, which you can, the way that you do it is by putting it in the maze, and then like telling it to wait a certain amount of time, and then like reading and averaging the IR values. Instead of just like on startup, it will just look around and read the values.
And for those of you doing EC3 later on, it is the same trick you can use in your code. Okay, are there any questions about what we went over today? There is a lot, and probably also very confusing, but yes.
Does the STM have multi-threading?
Yeah, we should.
I don't know.